Es graduado de la Facultad de Química de la UNAM, obtuvo su doctorado en bioquímica nutricional en la Universidad de Wisconsin, trabaja en el Instituto Nacional de Nutrición, inició el área de nutrición molecular y fue nombrado jefe del Departamento de Fisiología de la Nutrición. Se ha enfocado a las áreas de nutrigenómica y nutrigenética, y Armando nos va a platicar de los efectos de la dieta en la microbiota gastrointestinal. Armando, bienvenido, muchas gracias por acompañarnos.
Hello, good morning. Thank you for inviting me to this meeting, especially Dr. Kersinovich and Dr. Ostrowski. And what I'm going to present today is research that we have been doing in the area of nutrition and gut microbiota. This work has been conducted with Dr. Nimbe Torres. As we had an excellent talk about gut microbiota. The microbiota is a microbial community that lives in a specific environment. So, as it was mentioned, we have microbiota in the skin, in the mouth, and for this presentation, the gut microbiota is the central point of the presentation. The gut microbiota is very abundant, and as has already been mentioned, the main pillars of the gut microbiota are coming from Bacteroidetes and Firmicutes. And in terms of nutrition, the gut microbiota provides something specific for our nutrition. For instance, we cannot ferment or use complex carbohydrates, whereas we have some bacteria that they contain about 300 genes for different enzymes that can utilize these complex carbohydrates, and with this metabolism, we can absorb more energy from some products. However, the function of the gut microbiota depends on this balance between symbionts, commensals, and pathobionts present in the gut microbiota. In the health state, as I mentioned before, in addition to the energy extraction from polysaccharides, we have in this health state that the gut microbiota can help against pathogens, can provide some environment specific for the differentiation of epithelial cells in the intestine, and can modulate the immune response. However, when a disease appears, like inflammation, cancer, diabetes, obesity, autoimmune disease, this balance is affected, and this change in this balance is known as dysbiosis. In Mexico, we have a severe problem of obesity, and microbiota has been a central point in what is the importance of this microenvironment. Something that I want to show you is that we conduct a study in more than 1,100 people of Mexico City, and we found that 1 out of 2 Mexicans in this city, above 20 years old, they have metabolic syndrome. Metabolic syndrome, in order to define this, you have to use some criteria, and they are described in this slide. And in order to be considered as a person with metabolic syndrome, you have to have at least 3 out of the 5 elements of this alterations, such as elevated triglycerides, obesity, elevated glucose, hypertension, low HDL cholesterol, and associated with this is insulin resistance. If you treat these persons at this stage, it is possible to decrease these abnormalities. However, if you don't treat these patients, this will lead in the development of type 2 diabetes and cardiovascular disease. So, looking to these people with metabolic syndrome, if we make an oral glucose tolerant test, we observe that this is the curve for people, healthy, controlled people, and this is the curve for people with metabolic syndrome or morbid obesity. And we observe that there is a significant difference between this population. Also, the concentrations of circulating insulin are abnormal, indicating that these people, they have insulin resistance. What happened with the gut microbiota of these subjects? And first of all, we made an analysis of diversity of the gut microbiota. And as you can see with these graphs, this indicates the diversity of the gut microbiota, and in the upper part of these indicators is the gut microbiota of healthy people, and those with metabolic syndrome or morbid obesity, they tend to have lower diversity in their microbiota. If we sequence the 16S ribosomal gene in these persons, looking at the family or the genus level, we observe significant difference. Just looking the colors, you can see the changes. This is the area of people, healthy people. This is the distribution at the family level and the genus level of the gut microbiota. When they develop metabolic syndrome, this green area starts to appear. And also at the genus level, you can see this blue area is more present. And with morbid obesity, this green area is very high, and the blue area at the genus level is very high. And something that we have found is that particularly the Prevotella genus in these obese or people with metabolic syndrome is increasing, and the amount of bacteroides is decreasing. Looking specifically at the species level, we observe a significant decrease in Faecalibacterium prausnitzii in people with metabolic syndrome and morbid obesity, and an increase in Prevotella coli. Patrice Cani, he has demonstrated that everybody understands that obesity is a chronic state of inflammation, and this chronic state of inflammation is associated with an increase in lipopolysaccharides, circulating levels of lipopolysaccharides, that creates a status named metabolic endotoxemia. So we measure the concentration of circulating LPS in these people, and you can see that if they have metabolic syndrome or morbid obesity, there is an increase in the concentration of this lipopolysaccharide, and if we measure C-reactive protein, also we observe an increase. So these people, they have problems, and something that we ask, can we develop a strategy with functional foods and prebiotics for the control of this serious problem in Mexico by modifying the gut microbiota? And then something that we decide is to use some foods that can have the effect to modify this microbiota, even some ethnic foods that I consume in Mexico very abundantly, like chia seed, soya, nopal, oat, inulin. So I'm going to present some results about at least 2 of these foods and the effect on gut microbiota. Nopal is a food that is consumed in Mexico, and this food contains polyphenols, and in addition contains soluble fiber and insoluble fiber. What happened in rats that have consumed nopal on gut microbiota? You can see in this component analysis that those animals fed with nopal, they have different gut microbiota than those animals that didn't consume nopal. And the diversity of the gut microbiota, this is in blue, the diversity of the population that consume a high-fat diet compared to the control animals. But the addition of nopal in the diet restored partially the diversity of the gut microbiota. And also, we observed that there was a significant decrease in LPS circulating levels after the consumption of nopal. And particularly at the species level, we observed an increase in Bacteroides fragilis. Another food that we have studied is soy protein. We have demonstrated the metabolic effects of consuming soy protein. Particularly, we observed that soy protein decreases the expression of SREBP1, and SREBP1 is a transcription factor that modulates the expression of genes involved in fatty acid synthesis. And with soy protein, we have observed this response, reducing the accumulation of triglycerides in the liver and decreasing fatty liver. So what happened with the gut microbiota in rats that were fed casein versus soy protein? Something that we observe is that those that were fed with soy protein, they have different gut microbiota than those that were fed with casein. And something that was interesting at the phylum level is that you can see that this upper green area belongs to the Verrucomicrobia phylum. And consumption of soy increases this phylum. And at the genus level, the increase in Verrucomicrobia was associated with the genus of Akkermansia. So, we then develop a dietary strategy to treat people with metabolic syndrome using these foods. And this concept to use several foods that they make a metabolic change in people is known as dietary portfolio. So we make a combination of these foods, oats, soy protein, chia seed, and nopal, and we fed this and we treat people with metabolic syndrome with this dietary portfolio. After 2 months of treatment, we observe a change in the gut microbiota in these subjects. Particularly at the genus level, we start to observe a decrease in Prevotella and an increase in Bacteroides. And also at the level of the species, we observe an increase in Faecalibacterium prausnitzii and a decrease in Prevotella copri. Looking at the levels of lipopolysaccharide, we observe that after 2 months of consuming this dietary portfolio, subjects start to decreasing the circulating levels of LPS. This is the concentration at the beginning of the trial, people or subjects with metabolic syndrome, and this was the response after 2 months, and this was the response for people with morbid obesity. What happened with the metabolic parameters of these subjects? After 2 months, we observed a decrease in serum triglycerides and an improvement in the HOMA index, indicating that there was an improvement in the insulin-resistant status. Sorry, it's in Spanish, but it's easy to understand. So when subjects consume a high-fat diet with high sugar, there is a dysbiosis of the gut microbiota, increasing the amount of circulating lipopolysaccharides that activates a pro-inflammatory response, resulting in an increase in oxidative stress, inflammation, and a decrease in insulin sensitivity. With the consumption of these functional foods, we modulate the gut microbiota, decreasing the amount of circulating lipopolysaccharide and decreasing the oxidative stress, inflammation, and increasing insulin sensitivity. Something that we then ask is, for instance, in the case of soy protein, why soy protein is affecting the gut microbiota? And we know that soy protein contains dietary bioactive compounds, and these compounds are known as isoflavones. The main isoflavones are dietine, glycitein, and genistein. And particularly with genistein, we observe in mice fed a high-fat diet that after 3 months of dietary treatment, the glucose tolerant test, this is the response for a high-fat mice, with the addition of genistein, there was an improvement in the glucose tolerant test. This was associated with some changes in the gut microbiota, also at the level of Akkermansia mucinifila. And one question is, can we reproduce these effects in humans? So we conducted a clinical trial, and we studied a population with obesity and insulin resistance. And then to some part of this population, we provided a nutritional program with genistein, and another part of this population consumed this nutritional program with placebo. After 2 months, we obtained fecal samples, muscle biopsy, and made some plasma metabolomics. After 2 months of dietary treatment, something that we observe is that the consumption of genistein improves significantly the circulating levels of insulin, reduces the levels of HOMA, and decreases the levels of C-reactive protein. When we perform an oral glucose tolerant test in these patients, we observed that with the placebo we did not observe significant differences, but with genistein we observed an improvement in glucose tolerance, but particularly an improvement in the circulating levels of insulin. What happened with the gut microbiota in these subjects? Looking at the alpha diversity, we observed that before the dietary treatment, this was the diversity of this population, this is the baseline, and people that consumed placebo basically had the same response, but the addition of genistein to this diet increased the diversity. And the analysis of components show that the gut microbiota of those subjects that consume genistein was different with those or the baseline or those that were treated with placebo. So then, looking at the gut microbiota analysis, something that we observe at the phylum level is that this is the gut microbiota of all subjects. Half were divided and consumed placebo, and basically after 2 months of treatment, they did not change significantly the gut microbiota, but those that consumed genistein, they had a big change in the distribution of the gut microbiota, particularly the Verrucomicrobia phylum. And this change in Verrucomicrobia phylum was associated mainly to changes in Akkermansia mucinifila. As a consequence of the consumption of genistein, subjects, this was the baseline concentration of LPS, was significantly reduced with the consumption of genistein. And then we made some metabolomics, in order to measure what kind of changes were observed in the gut, in the serum associated with the gut microbiota, and the consumption of genistein modifies some metabolites that are circulating in the blood. As they are mentioned here, we are studying now what is the impact of these metabolites in the physiology of a subject. Finally, we make a sample. We obtain a sample of skeletal muscle from these subjects, and we make a gene expression array, and we observe that those that consume placebo had very different expression of genes than those that consume genistein, and basically these changes were associated main part to the alteration in the expression of this enzyme AMPK, and AMPK is associated in one part with fatty acid oxidation. So in these tissue samples, we measure the mitochondrial activity, and this was staining with succinate dehydrogenase staining, and the darker, the higher the activity of the mitochondrial activity, and you can see that with genistein there was a substantial increase in the activity, and this was associated with an increase in the phosphorylation state of AMPK. And the last part was just